So this is a model of an atom. We've got a nucleus made of protons and neutrons. The protons are blue, the neutrons are red, and the electrons are orbiting around the outside. We're not really interested in the orbiting electrons at the moment, so I'm just going to get rid of those. So in radioactive decay, something happens to the nucleus. Not the atom as a whole, but the nucleus. And our first type of decay is alpha decay. And that's when a small bit breaks off. And the bit that broke off consists of 2 protons and 2 neutrons. That is alpha decay. We're left with a slightly smaller nucleus, one that has 2 fewer neutrons and 2 fewer protons. Because the number of protons has changed, it changes into a new element. So now we have a different nucleus, and this one is going to undergo beta decay. And that's when a neutron decays into a proton plus an electron, and the electron is ejected at high speed. In this case, the number of neutrons changes, goes down by 1, but the number of protons increases by 1. And because we've got a different number of protons, a different atomic number, again, we have a new element. Finally, in gamma decay, the number of protons and the number of neutrons does not change. All that happens is that some energy is released, which makes the nucleus more stable. Because the number of protons does not change, the element does not change. In chemistry, you'll have learnt about chemical equations, how you can use the symbols to show what is going to be present before a reaction and after a reaction. And we can do something very similar with nuclear equations. We can represent alpha, beta, or gamma decay in an equation form. Now, to do that, you need to memorize 3 sets of symbols, which is the symbols for alpha, beta, and gamma. Now, we're looking at page 11 in your notes here. It says alpha radiation. Well, we know the symbol for alpha. It's alpha. We know it has 2 protons and 2 neutrons. So it really has an atomic number of 2 and a mass number of 4. And that is the same as a helium nucleus, so we can also write that as 42He. We can do something similar with beta. Beta, as you've already seen, we represent as -1 and 0. It has no protons or neutrons, so it has 0 mass number, but we'll give it a -1 atomic number because it consists of an electron, which is negatively charged. It is produced when a proton is produced from a neutron, and so to balance out an equation, as you're gaining a proton, you have to gain a negative proton, which is the electron. That's not strictly what's happening. An electron is not the same as a negative proton, but for the sake of these equations, that's sort of how we treat it. Because it's an electron, we can also write that down as 0 - 1 E. Gamma, the symbol gamma, like that, has no particles. It has no protons, no neutrons, so we can write it down as that. Very rare that appears in equations, but it has appeared in the past, so we will have to learn that. You must memorize those 3 sets of symbols. Now, we can use these symbols to represent alpha decay, beta decay, and gamma decay. So let's say in alpha decay, we start off with some radioactive element, X, don't know what that is, and it's going to decay into something, we don't know what it is, we're going to call it Y. It's not yttrium, just X turns to Y, and it also gives us an alpha particle. Now we also know that the alpha particle has these numbers 4 and 2, and the particle X has a mass number of A and an atomic number of Z. We don't know what they are yet. What you'll often have to do is work out what is the new mass number and new atomic number of this daughter nucleus, this nucleus that has been left behind after the decay. And it's very simple to do. All you have to remember is that in the top line, the numbers on the left side of the equation must balance with the numbers on the right side of the equation. So we start off with A, there. We've lost 4 particles from that. So this number here is going to be A minus 4, whatever that happens to be. The bottom line, similarly, we have to make sure that the numbers match up. So we start off with Z. Now we're going to have Z minus 2. So whatever number we start off with, we subtract 4 from the mass number, subtract 2 from the atomic number, and that means our equation is balanced. And we'll have a look at an example of that in a second. Beta decay, we treat very similarly. We start off with our particle X, different particle, but X, and it has the same mass number and an atomic number. It's going to decay into some unknown particle plus a beta particle. And again, we're just going to balance the numbers. So the top row, A equals what plus 0, what's going to be A. The mass number is unchanged. Well, this number minus 1 equals Z. So this is going to be Z plus 1. So the atomic number is going to increase. And that's because we're getting an extra proton. And again, we'll see one example of that in a minute. Finally, gamma decay. It's a bit odd because it doesn't really involve any extra particles. We've got A and Z again, and it's going to turn into, well, we're going to have a gamma particle released. Well, 0 and 0, the numbers are going to stay the same. And because the mass number hasn't changed, it's going to be the same element. So we don't actually get a new nucleus released. What's happened is that this gamma particle is just energy that is sent away. So there's no real change in the structure of the nucleus. Sometimes we see a little sort of asterisk, which represents just that it's what's called an excited nucleus. It has a bit more energy than it wants, and it needs to get rid of that energy as a gamma particle or a gamma wave. So note that gamma decay does not result in a new nucleus. Gamma radiation is produced when an excited nucleus loses energy. So let's have a look at some examples of this. It's important to remember that a particle that undergoes alpha radiation is probably not going to undergo beta as well. It'll be different starting nuclei. However, what often happens in real life is that we start off with a radioactive particle. It decays by, let's say, alpha, and then the product, the daughter nucleus, might also be radioactive, which can decay by beta or by gamma, and so on, and we can get what's called a decay chain. But we're just going to look at individual decays. So uranium-238 is our first one, uranium-238. And 238 is the mass number. The atomic number for uranium is 92. You will not be expected to memorize any of these. Now, you might be told that this decays into thorium by alpha. And what you would need to do is to fill in the missing numbers. So you could be given all this information in an exam and you just have to fill in the numbers. Well, the only ones you have to memorize are alpha. And you should know that as 4 and 2. So the mass number of thorium, we start off with 238. We end up with this plus 4. So what plus 4 equals 238? It's 2, 3, 4. Similarly, if we do the bottom row, 92 equals what plus 2? 90. And so now we're left with the atomic number and the mass number of thorium. If you didn't know what the name of the element is, you could always look at the periodic table, because you'll work out the atomic number, and the atomic number defines what the element is. Beta decay, we can do something very similar. This time we're going to use carbon-14, which has an atomic number of 6. And it decays by beta decay. We know beta is 0 and -1. 14 equals watt plus 0. That's going to equal 14. And 6 equals watt minus 1. That's going to be 7. And if we look up the periodic table to see what has an atomic number of 7, that's nitrogen. So carbon-14 decays into nitrogen-14, which is the bog standard nitrogen that we get in our air. Makes up 79%, 78% of the atmosphere. So carbon-14 turns into nitrogen and emits a beta particle. So in summary, whenever you're doing a decay equation, what you need to memorize are these things: 4,2 alpha, 0 minus 1 beta, and 0, 0 gamma. They're the only ones you have to memorize. And then you have to balance the numbers on the top line, the mass numbers, balance the numbers on the bottom line. Do not forget that the mass number, the larger number, always goes on the top line. The smaller number, the atomic number, always goes on the bottom line.